What does a bolt of lightning, a campfire, an ion engine, and a nuclear fusion reactor have in common? They're all examples of plasmas. Plasma is one of the weirder states of matter, and one that most aren't very familiar with, but understanding how they work allows for some amazing processes to be possible. This video is about plasma in its many forms, and how we can first make it, and then learn to harness it to build functional devices. From fire to fusion, there's a lot to cover, so let's hop right in. First, to understand what plasma is, let's look at the simplest way to make some. When you strike a match or a lighter, you've just made a small amount of plasma, which we call fire. Fire is the result of a chemical method for producing plasma. When you first strike a lighter, tiny, superheated pieces of flint are sprayed over a small tube where butane is being released. When the sparks touch the butane, and the mixture of butane and oxygen in the air is just right, a chemical reaction is kicked off that releases a tremendous amount of energy. All this energy rapidly superheats the mixture of gases and air. As the atoms get hotter and hotter, eventually they have so much energy that the electrons orbiting around the atomic nuclei can't hold on any longer, and they start to jump energy levels and eventually fall off. It's almost as though the atoms themselves are melting. This process, known as ionization, leads to a very complex mixture of electrons, ions, and a huge assortment of molecules with a variety of charges known as radicals. This soup of charged particles is what we call plasma, and has lots of interesting properties. For example, it's very conductive and allows electricity to flow through it easily. The energy released in this chemical reaction isn't enough for the nuclei to melt apart though, so they stay intact and no new elements are created. As everything ionizes, energy is released until eventually there's not enough left to continue to ionize things, and everything recombines, leaving only hot gas behind. In the example of fire, the energy that allows things to ionize comes from the chemical reaction of burning butane. But if you provide the energy in a different way, you can still produce plasma. One way to do this is through the use of high voltage electricity. Lightning is a great example of this. As static charge is produced in the clouds, massive quantities of electrons build up in the lower part of the cloud. This highly negative area repels electrons in the ground below, inducing a net positive charge. Sometimes, the intense electric field generated can cause the air around sharp objects on the ground to leak charged particles. These can then ionize the air and produce a small amount of plasma called a coronal discharge. When this happens, it's known as St. Elmo's fire and has been seen on boats for centuries. Often, so much charge builds up, a long stream of positively charged particles will start to grow, called an upwards leader. These leaders will be produced all over the area under a lightning storm. In the clouds, so many electrons will build up that they start to actually repel themselves. A stream of electrons called a streamer starts to grow and branch out of the cloud until one connects to one of the growing upwards leaders on the ground. In the instant of this connection, all of the built-up electrons flow down the connection as if it were a wire, allowing the charges to equalize and producing a bright flash in the process. As they flow, the electrons smash into air molecules, knocking off more electrons and producing plasma. For every centimeter of air, you need about 10,000 volts for that connection to happen spontaneously and an arc of electricity to be produced. If the voltage is too low, the electrons don't have enough energy to push their way through the air and just get stopped before a connection is made. This is known as the breakdown voltage and is closely related to the pressure and type of gas or material in the way. Keep this in mind as it'll be important later. In lightning, the voltages involved can be upwards of millions of volts, which is why lightning bolts are so large and can be started from such great distances. Making bolts of lightning like this in a home or lab setting is actually fairly easy, though obviously not nearly to the same scale. Of all of the devices that can produce large bolts of electricity, Tesla coils can produce arcs that are the most similar to natural lightning. Depending on where you live, the electricity that comes out of the average wall socket is usually in the range of 120 to 220 volts. A Tesla coil steps up this voltage to several million volts, allowing huge arcs to form easily. However, we want to learn to use plasma to build functional devices, and while Tesla coils are cool to play with, they aren't super useful for making these as the voltage is actually too high and the current too low for most applications. If we want to use plasma to make anything more than a decorative plasma ball, we need to build a high voltage system that we can control and that puts out a more reasonable voltage. A system like the one we're going to build can be used for a wide range of applications, though we'll be focusing on two in this video. The first will be a small demonstration fusion reactor, and the second will be a device called a magnetron, which is used in semiconductor manufacturing. We'll get into how these work later, but first let's build our high voltage system to power them. The core of our system will be a large transformer. These devices can step up a low voltage to a higher one at the cost of some current. Luckily, home electricity can come in more than 10 amps, so there's plenty of current to spare. A transformer is made of 2 coils of wire wrapped around an iron core. The voltage will change in proportion to the number of turns of each coil and the ratio between them. If you have 100 turns on the input side, also known as the primary, and 2000 turns on the secondary or output side, the output voltage will be about 20 times higher. So if you put 100 volts in, you get about 2000 volts out. It just so happens that a transformer inside every microwave does exactly this. Microwave oven transformers, or MOTS for short, are super easy to find online or by salvaging from a broken microwave. They're pretty tough, so chances are if the microwave is broken, the transformer is still fine. I won't go into how to extract them in this video, as there's already lots of videos on how to do this on YouTube. A word of warning though. Everything from this point on is extremely dangerous and should be done only with extreme caution. While MOTS are high voltage, they're also very high current and will kill you very quickly if you touch one while it's on. The simplest way to wire up a MOT is to cut one end off an extension cord and after stripping the wires inside, connecting the hot to one side of the primary and the neutral to the other side of the primary. The ground wire can be ignored if your extension cord has one. I would also add a switch to one side of the circuit or plug the end into a power bar that has an on-off switch. This way you have a faster way to kill the power should you need to instead of having to rip the plug out. Wiring up the secondary can be a little weird, depending on the model of transformer you happen to get. If you're lucky, you'll get a transformer with 2 output wires, but occasionally one side is soldered to the main body of the transformer. If this happens, just solder a wire to it and be extra careful not to touch the outside of the transformer while it's running. In either case, add a wire to each side and everything's set up. For the devices that we want to build, there's a lot of problems with our setup that need to be addressed. First, there's no way to control the voltage precisely as it can only be turned on and off. For simply making arcs, that's fine, but for devices that use plasma to do something, like in semiconductor manufacturing, there needs to be a way to control it. So to do that, we need to add a piece to the primary side of the transformer. Ideally, you'd use something called a variac, which is a weird kind of transformer that allows you to throttle voltage between 0 and 120 volts. By putting it before the primary, we can change the voltage going into the transformer and subsequently the voltage coming out. However, variacs, especially the good high current ones, can be hard to find or expensive, so instead we're going to use a homemade device called a scariac. Over at the King of Random, Grant Thompson made a great video on how to build one of these, so be sure to check out that video for more info. When we were building our system, we couldn't find all of the parts he used, so we changed the design a bit to work with what we had available. Instead of the pulling mechanism in the original video, we went for a rotating version. The way this works is pretty simple. As the lever is turned, it brings 2 copper electrodes closer together or further apart. They're placed in a tub of baking soda solution so electricity can flow between them. As the distance between the electrode decreases, so does the resistance, allowing more current to flow. If the electrodes are allowed to touch, the maximum amount of power will be allowed to flow through. Here you can see we can control the speed of a motor that's been connected directly to our scariac by turning the dial. There's one last change we can make to the primary side of our high voltage system, which is to add a current limiting device called an inductive ballast. This will prevent too much current from flowing through our system and potentially blowing things up later. All it is a second MOT, but this time the secondary is shorted out and the primary is placed in series with the primary of our main transformer. So for our system, the output of the scariac is fed into one side of the inductive ballast, and the other side is connected to one side of the other MOT. For more information on how inductive ballasts work, I've added a link in the description. Now we can look at the output side of our system. As it stands, everything thus far has been alternating current. This is why I've been referring to the 2 wires as the hot and neutral rather than positive and negative. In alternating current, there's no positive or negative since the electrons are moving back and forth rather than in a circuit. For vacuum-based plasma devices, we usually need a direct current so that electricity flows in a consistent direction. This will allow us to control what happens to the plasma and the motion of the particles inside it. So to go from AC to DC, we need something called a full-wave bridge rectifier, also known as a diode bridge. All it is 4 10 kilovolt diodes arranged in a diamond pattern like this, making sure that the input and output sides of the diodes are lined up correctly.
The input is here and here, and it doesn't matter which output wire of the transformer is attached to which side of the diode bridge's input. The output of the diode bridge does have a distinct positive and negative side since everything is now direct current. The short version of how this works goes like this. Alternating current is a sine wave that goes from plus 2000 to minus 2000 volts. The diodes essentially flip one of these peaks over so that the current can only go from 0 to approximately plus 2000 volts. I've added a great little tool in the description that makes it very easy to visualize what's actually going on, so be sure to check that out and mess around with it if you want to learn more.
One final touch would be to add a capacitor across the output of our diode bridge. This smooths out the peaks into a nice stable DC voltage rather than pulses. This is because the capacitor holds and releases charge, so while the next pulse is rising, the capacitor is still slowly releasing power, compensating for when the voltage is low. This is entirely optional but recommended. Always be sure to discharge a capacitor by shorting the two terminals before putting your hands anywhere near it. For our system, the capacitor from a microwave would be perfect for this.
And with that, our high voltage system is done. We're now well on our way to building our plasma devices. But before we can build them, we need to talk about pressure. Earlier in the video, we talked about the breakdown voltage of a gas. This is the amount of electrical potential required to force electrons through a gas, and it's closely tied to the pressure. If we decrease the pressure, we're effectively removing millions of atoms of gas, so there's a lot less stuff in the way. The lower we make the pressure, the easier it is for electrons to flow, and the less voltage is required. For devices like Fusors or Magnetrons, they require a fairly deep vacuum to function properly, far deeper than anything you'd experience in day-to-day life. To reach these pressures requires at least one special pump. The more serious the application, the more complex and powerful the pump needs to be. For the purposes of this video and learning the basics, we're only going to use a mechanical pump. In this case, we're using an Edwards rotary vane pump capable of reducing the pressure inside a chamber to at least 10 to 100 millitorr. Torr is a measure of vacuum, where 1 torr is about 1/1000th of atmospheric pressure. Our pump needs to be able to reduce the pressure to 1/10,000th to 1/100,000th of atmospheric pressure. I've used both an Edwards Model 2 and a Model 5 successfully for this, but many others will work as well. A cheap vacuum pump usually won't cut it though, so make sure to check the pressure it's rated for before buying one. If we wanted a deeper vacuum, or we were going to be letting lots of gas into the device, we would put a secondary pump after the mechanical pump. These come usually in two forms, diffusion pumps and turbo pumps, and we'll talk more about how they work and when they're needed in a future video. Now that we've got our pump, we'll need a chamber to contain our vacuum in. Previously, I made a video on how to make such a chamber out of common glass jars, and I've put a link in the description. All we need now is to connect our pump to our chamber and add the high voltage system we built earlier. The actual plumbing for the vacuum system is fairly straightforward, though it'll change based on what device you plan on building and its requirements. In our case, we ran a line from our vacuum pump to a T-barb. One side of the barb was connected to a short length of tubing and then to a valve. The other side of the valve had another short length of tubing and a straight barb on the end. This will allow us to attach a balloon to supply gases, as well as to vent to atmosphere. This isn't ideal, but we're working with what we had. In other systems, I've added a line that can be attached directly to tanks for specific gases. The other side of our T-barb went first to a vacuum gauge and then into our chamber. Now, a note about materials. When you build a vacuum system, you're going to start to run into all sorts of problems that will affect how deep of a vacuum you can easily pull. For example, most materials have a property called outgassing when placed in a vacuum. This means they slowly release small amounts of stored gases and volatile molecules that will screw with your pressure. So it's important to only use materials suited to vacuum work. This usually means as much metal as possible, but some plastics are also okay. Vinyl is usually okay for tubing, and I haven't had many problems with it, though I would suggest getting the kind that has reinforcement built in, or it'll tend to collapse under the pressure. When it comes to adhesives to stick everything together, the best off-the-shelf product is easily JB Weld. It's come to be known as the duct tape of the vacuum world because of how effective it is when chasing leaks. It can also be baked up to 500 degrees, so if you need a deeper vacuum, you can actually bake your chamber to force any remaining volatiles out before you turn on the vacuum pump. In a future video, I'll go through all the ways to chase leaks and troubleshoot systems like this. Finally, we've got all the pieces we need to make our devices work and can move on to final assembly. To see all the pieces work together, let's first look at fusors and how they're set up. A fusor is the simplest form of fusion reactor and is basically just two electrodes, one inside the other. The central one is connected to the negative side of our high voltage system, and the outer is connected to the positive side. Before we can turn on the power, we first need to turn on the pump and let the pressure get as low as possible. This can take a few minutes, so be patient, but if the pressure doesn't come even close to the 100 millitorr range, you've definitely got a leak. When most of the gas is removed, the high voltage can be turned on. When this happens, electrons immediately start flying across the electrodes, smashing into the small amount of gas molecules left in the chamber. This ionizes the gas and gives the nuclei a positive charge. These positively charged ions are attracted to the negatively charged inner electrode, and so the nuclei start to accelerate toward it. If we were to supply enough voltage, the ions could have enough energy that when they smash into each other, they would actually be able to fuse into heavier elements. However, our system's capabilities are far lower than what's required for that purpose, as that would be very dangerous without extra precautions. In a future video, we'll build an upgraded version of this system capable of that and get into the specifics of how to achieve fusion while staying safe. We'll also explore other models of reactor that are far more complex and how they work. If everything has been wired up correctly and there's no leaks in the vacuum system, the whole chamber should fill with plasma when it's turned on. To show how important the pressure is, here's what happens if I let a little bit of gas into the chamber while it's running. The plasma quickly retracts to only the inner grid as the electrons can't travel very far as there's too much stuff in the way. When I first started building fusors, I didn't have a strong enough pump as I was using the compressor out of a fridge, and this retracted plasma was all I could make. When I finally switched to a proper pump, the glow I was greeted with was a magnificent sight that I'll never forget. If you're interested in fusors, you may also want to check out the Fusor.net forums. There's a lot of great information on how these devices work and some amazing builds people have done over the years. Fusors are a great example of how you can control the flow and motion of charged particles by using electric fields. Positive charges move towards negative electric fields and vice versa. But charged particles can also be manipulated by magnetic fields. When I built my first fusor, I noticed this was possible when I would put magnets near the chamber and could see the plasma getting dragged around. If we take the idea further, we get to devices like magnetrons. Rather than an outer and inner grid, magnetrons, or at least the version we'll be making, simply have a top and bottom electrode. In this case, the bottom is an aluminum plate which the chamber is resting on and is connected to the negative side of our high voltage system. By placing a pair of magnets underneath the bottom plate, we can bend the plasma into a tight ring. Here you can see the magnetic field of the two magnets visualized using some MagnaView film. The ring of plasma superheats the metal it's in contact with and causes it to sublimate or turn directly into a gas. If we put a substrate like a microscope slide or a piece of metal above this, it should get coated in a very thin layer of metal. However, getting them to actually do this can be extremely difficult as they're very sensitive to pressure. They must have a pressure of no more than 100 millitorr, but even that's not usually good enough. 1 to 10 millitorr is closer to what's needed to function properly, and at these levels, chasing outgassing becomes a nightmare. If you're going to build one, I would highly recommend using a secondary pump to help keep up with all the outgassing. In a future video, we'll explore how to troubleshoot magnetrons and get them working, as they're easily the pickiest vacuum device I've ever attempted to build. They'll really need a whole video just to work on the troubleshooting. When they're functional, their uses though are extremely broad. I originally wanted to build one so I could coat objects in titanium nitride, as it's extremely tough and also biosafe, so it could be used to make implants. Let's review what we've covered in this video. Plasma comes in many forms and is made of a soup of charged particles. It's produced when a material, usually a gas, is given so much energy that the electrons melt off of the nuclei. The energy can be chemical or electrical, and the properties of the plasma greatly depend on its composition. Given sufficient energy, the ions in the plasma can be coaxed into smashing into each other and fusing into heavier elements. Plasma can be used to evaporate metals and is important for everything from semiconductor manufacturing to medical implants. I hope this video has served as a good introduction to the world of plasma physics and all of the amazing things that can be done with it. We'll be revisiting and expanding on a lot of the topics covered in future videos, so this was meant to act as a primer for that and to give you some ideas of how these systems work and how it's possible to build them yourself. I've been working on these sorts of systems for 8 years now, and they never cease to amaze me. They're tricky to build, but when they work, the results are breathtaking. With the basics covered, I look forward to exploring other techniques in the future. Everything from electron beam evaporation to ion engines. So be sure to check back every other Monday for all of that.
That's all for this video. I hope you've enjoyed. If you have and want to see more DIY physics videos, be sure to subscribe and consider clicking the bell to get email updates when I post new videos. If you've got suggestions for future videos or other devices you think we should try and build, be sure to leave them in the comments down below. As always, I love reading your suggestions and take them into account when choosing new projects.
If you'd like to help the continued production of science videos like this one, I'd really appreciate if you check out my Patreon. Every penny that I can put towards videos will make them better. Thanks, and I'll see you next time.